we are going to use the medium which is conductor. So conductors are basically, when you talk about them, when you take from the periodic table, they are metals, right? So when you take these metals, what is the first thing that comes to your mind? What do conductors possess? They possess something called as free electrons. So these free electrons are the ones which are going to be in motion, right? But we know the fact from the basics of motion that for you to put an object into motion, right, what are we supposed to do? We need to do some work, right? So let's try to first visualize before we directly get into the concept of the terminologies that are used in this chapter, right? So if I take a conductor like this, then what do these conductors contain? They contain free electrons. They have many such electrons. Why do we call them as free electrons? Because they possess the capability of moving within the conductor, right? So I'll tell you the story. What happens initially is, if at all you go and buy a wire from a shop, let's say you have a conductor. In that conductor, you will have free electrons. See, generally what we think is the electrons inside the conductor are going to be stationary, but that's not going to be the fact. So the electrons inside the conductor will be in motion only. So this is where the confusion starts. How is this possible? You just went, you bought a wire, then if it is going to be conducting, we are supposed to get shock, right? So anything we touch, we are supposed to experience a shock because the charge is going to pass through your body as well, right? But why is that not happening? Because the motion that is happening here is not an aligned motion. It is a random motion. And why is this happening? Because of thermal agitation. Means because of the temperature that is present around us, these free electrons have the tendency to move around in the conductor, within the conductor, but not in an aligned path, rather in a random path. So the motion will be in such a way, right, that each electron is going to definitely have some velocity because it is in motion. But the velocity, if I call them as U1, let's say I call this as U2, something like this. Let's say there are n electrons that are present. Then U1 plus U2 plus U3 plus so on till Un, everything taken in the vector form is going to be a 0. Right? Actually speaking, the average of all these values will be a 0. So what is happening here? The vector sum of all the individual velocities, which is possessed by the electrons, which are randomly in motion, will be summing up to a 0. Now, from here, our story starts. Right? So since these conductors are in motion, I cannot give a name called as current. Because the name of the chapter is current electricity. When I told current means, when I say the electrons are supposed to have motion, I cannot call this as electric current. So for me to give a name to it called as electric current, I need to do something. What we need to do is first make this random motion an aligned motion. If that should happen, the first thing that we need to do is supply some energy to it. So basically, when you have a wire, right? So let's say a wire is connected to a bulb like this. This is a wire. Inside this, what is happening? This random motion is there. So inside this wire, the random motion is still taking place. But what will happen? Will this bulb be able to glow? No, it will not be able to. So what are we supposed to do? What do we logically do in the first place? You take it and connect it to a device like this. You connect it to an active device, which we call it as battery, about which we'll be seeing slowly, right? So when you connect it to the battery, what has happened? This whole thing is given a name called as circuit. Now the circuit has become a closed circuit, due to which there is going to be continuous motion of electrons taking place, which supplies the energy to the bulb and making it glow. Right? So that's what happens. That's what we do in our day-to-day life if something like this is to be achieved. Right? This is where the question starts. So you connected a battery and something is glowing, right? What is the actual science involved behind it is what we are going to answer in this chapter. Okay. So what is the logic here? The electrons which were having random motion, right? So the electrons which were having random motion like this u1, u2, un, something like this. Then what will happen is when you connect it across a potential source, when I say potential source, you have a positive terminal here and a negative. It can be reversed also. So for understanding, basically I took left side to be positive and right side to be negative. Now let's think of the logic. So whenever you connect a potential source, listen, this is where I need you to be slightly mature. Like when we connect a potential source, obviously it is going to have an aligned path. But what we need to do is we need to take the knowledge of our previous two chapters and apply it here. When I have a positive terminal here, negative terminal here, first thing that will happen is there is going to be an electric field that will get generated. From which side to which side? Electric field is always directed from higher potential to lower potential. So when these electrons which are there inside the conductor are placed within the electric field, what will happen to them? Obviously, they will start experiencing a force of how much value? E into capital E, because I'm talking only about the magnitude. So charge multiplied with the electric field that is present is going to give you the amount of force that is experienced by the particle. But according to Newton's law, this force is also equal to m into A. Means if I take this A will be equal to small e into capital E divided by m. And one more point I want you to notice here, the kind of battery that I have connected is a DC battery. DC is direct current. Right? You know that there are two types of current. What are they? One is direct current and the second is alternating current. I would like to give you a small clarification because I'll be connecting that dot to hit this one. So when I talk about direct current, if I take this to be the current and this to be the time, this basically I'm trying to draw a graph which shows the variation of current as a function of time. So how does a direct current look in terms of graphical representation? It is going to be something like this. Can I call it as direct current? If you connect a 5-volt battery, there is going to be a constant supply of current that is going to take place. Okay, means the current is not changing with respect to time. So that is the perspective. When it is not changing with respect to time, we call it as direct current. So this gives rise to another important question. If this is direct current, can I call this as direct current? So what did I tell you is the definition of direct current? What is that you people know in the first place? What is direct current according to you? You mean to say direct current? You mean to say the current value is not changing with respect to time, right? That's what we think is direct current. So here what is happening is the value of I is changing with respect to time. So this cannot be direct current. Am I right? But that's where we make mistake. This is also DC only. So this is where we need to slightly know another important point. Direct current doesn't mean that the value of current is fixed with respect to time. It means it is unidirectional with respect to time. So what do I mean by unidirectional is it flows only in one direction. Whereas if I talk about a current which is varying like this, where you have a positive terminal, negative terminal, positive terminal, then you call this as an alternating current. So look at the difference in the graphs. This kind of a direct current is called as fluctuating DC. So I want this to get erased from your mind. Direct current doesn't mean that it is having a fixed value with respect to time. Rather, direct current is unidirectional current. It is unidirectional. Whereas alternating current is bidirectional. So what is the current that we are getting at home? We are using these plug points and everything. No? What current is this? Is this AC or DC? All these plug points. This is actually AC only. AC. What we get at our home is alternating. It will be given when you buy the plug points and everything. It will be given 230 volt AC. 230 volt, 50 hertz in கொடுத்திருப்பாங்க. Hertz is possible only for AC. You have a frequency associated, no? So bidirectional current is what is called as alternating current. Right? I hope this point is registered in your. Right? See, to put it simple, right? You go to a shop. Everybody would have seen this kind of a battery. You go and buy. Right? For those who are online. So you have two terminals here. What are they? You have a positive terminal, the one which is extended outwards is a positive terminal, the flat one is a negative terminal. Then you have the potential that is available on this battery. Generally, it will be written. What is that you are able to see? What is the potential difference you are able to see? It is a 1.5 volt battery. It will be written there. Okay, it's a 1.5 volt battery. And here there is a name written, which is called as AAA. So generally, when you speak in, like you go to a shop and you don't, when you go to a supermarket, right, especially if you go to an electrical shop, they'll understand this potential difference and they'll ask you how many volt battery you want. But generally, you want to convey it to someone who doesn't have knowledge about it, you convey it as a AAA battery. Right? You convey it either as a AAA or a AA battery. Have you heard of these terms, AAA and a AA? So both will have same kind of potential also. You can always look at it next time. So here it is written as 1.5 volt. What is the meaning of this 1.5 volt is? This positive terminal has a potential. Negative terminal also has a potential. So listen to this very carefully. Each point will have a potential. And the difference between the potential of those 2 points is what we call it as potential difference. So this 1.5 volt which is written here is actually the difference between the potential of the positive terminal and the negative terminal. And when it is going to be a battery which is a DC source, this is a DC source. Because why did I say it's a DC source? You asked me, how to find it. It is written as 1.5 volt. There is no frequency given beside it. So if the frequency is given, then it is considered to be a AC device. So that is why next time, right, whenever you are buying any kind of electrical device, suppose you go to a shop, there is a difference. You go to an electrical shop or an electronic shop, right? You buy a device, there will be something called as power rating written on top of it. Along with that, they will tell you what is the operating voltage for. Means how much voltage can we supply. For example, if you're going to use a device in India, let's say these lights and everything, you're going to use it in India, they will be operated at 230 volt. It will be written as 220 to 230. Okay, whereas if you use the same thing in US, right, it's going to be 110. That is why the difference in charges and everything, the way you can think like, why are we unnecessarily using two different things? That is how it is designed. You need to increase the value or decrease the value depending on the place you are. See, for example, you buy some product in US and come, it can be operated only at 110 volt AC. Okay, that's called an RMS value, about which I'll tell you in the 7th chapter. Okay, so as of now, remember this, there the voltage is 110. Okay, can we use the same thing here? No. Why? Because you are supplying more, the device will blast like anything. See, for 110 device, you are giving 230, almost double the value, more than double the value. It cannot take it. Is obviously going to burst or anything can happen. It will get damaged for sure. Right? So what you need to do is you need to bring down the voltage. From 230, you need to bring down the voltage and then use it. For that, we use a device called as a transformer. Okay, I'm just introducing all these terms so that when we see those terms, you'll understand things better. Are you able to understand? So, similarly, you buy a device here, you want to use it in US, what are you supposed to do? You need to increase the power rate. Because there only the plug point is able to supply only 110. But you want 230 volt for it to work. You need to increase its capacity. Are you getting some perspective? You'll understand about it in 7th chapter. Okay, that time I'll tell you again. But now, did you get some perspective about what is AC and DC? There is a reason why I stressed on that point. right? So basically, when you talk about direct current is, can you tell me the right word? It is unidirectional. If somebody asks you, don't say the value is fixed. Unidirectional currents are called as direct currents. Bidirectional currents are called as alternating current. Okay, that is one thing. Now, that story, how is it going to get linked to this? Is what we are going to see. So I told you E into E is going to be the force. That force is equal to mass into acceleration. So A is equal to small e into capital E divided by m. Small e is the charge of the electron. Capital E is the electric field that is generated due to the potential difference. Right? There is an electric field from the positive to the negative terminal. Right? So it is getting created, and mass is the mass of each electron. Am I right? So if you observe, one point that I told you is the initial velocity of each electron is different, and they are in random directions as well. Whereas, if you look at the acceleration of each electron after the battery has been connected, it is the same for all the electrons. Why? Because charge of every electron is same, the electric field that is getting generated inside is same, and mass of each electron is same. So overall, this value is going to be a constant. Am I clear with this? Right? So this is going to be the acceleration which is experienced by each electron which is present in this circuit. Right? To put it simple, yeah, which is present inside this conductor. Now, the point is, I have applied potential difference here. Can I say that there is some work that is being done? So when you apply a force on an object and the force is causing some displacement in the direction of application of force, you say work is done. Here, the work is done like this. See, if you want to define the potential difference, then V is written as the amount of work done per unit charge. See, this is something you have already seen in your 10th grade. That is why I'm touching upon all those points. So how is potential difference defined as? It is defined as the amount of work done per unit charge. So work done is measured in joule and charge is measured in coulomb. This joule per coulomb is what is called as volt. This volt only we saw there. 1.5 volt. Okay. Now, by you applying this potential difference, what is actually happening? There is current present in this circuit, right? So, how do you define this current as? Current is defined as the rate of flow of charges. Rate of flow of charges. So, how do you write this as? You write this as Q divided by T. All right. It is going to be Q divided by T. So, when you talk about this current, it is written as Q by T because something measured with respect to time is rate. Rate of flow of what? Charges. That is why charge is in the numerator, time is in the denominator. So, charge is measured in coulomb, time is measured in seconds. So, this coulomb per second is given a name called as ampere. And the symbol for ampere is going to be capital A. So, this is also a known fact. You know this already, right? Now, the extra point that you need to know is when you talk about the type of current, right? So, apart from this AC and DC, right, there is another way of understanding it also. I would not say understanding. There are two other types as well, where one is called as average value and the second is called as instantaneous value. Right? So, when I talk about the average current is defined as the rate of change of, the rate of flow of charges, delta Q divided by delta T. Am I clear with this point? Similarly, if I have to speak about I instantaneous, it is written as dq divided by dt. So it is the rate of change of instantaneous charge. Means this charge q will be a function of time. This charge q will not be a function of time. Okay. So this is going to be two other currents that you're supposed to know. If I say q is equal to pi t square plus 2, you observe this charge is a function of time. So I'm going to ask you, what is the value of current at t is equal to 3 seconds? If I put a question like this, what are we supposed to do? Whenever you see the word at, it means it is the instantaneous value. So what you need to do is, you can only find I instantaneous, which is given as dq divided by dt, which is 10t. So 10 into, in the place of t, what will I substitute? I'll plug in this 3, answer will come out to be 30 amp. So this is what happens. So this is going to be the value of electric current for this kind of a charge flow at 3 seconds. So every instant you see it keeps changing. This is what is alternating current. I'm sorry, correction. This is actually not alternating. It's just changing with respect. It is unidirectional. The first derivation in this chapter. Okay. So when I take a conductor, don't write the heading, leave some space for the heading. We'll give a name to it after we derive at that value. Okay. Let's say you have a conductor which has the free charges flowing inside. The free electrons which are flowing inside it in a random direction. This is U1, this is U2, this is U3, so on. If you take this to be negative, it will be UN. If this is going to be positive charge, this is going to be negative charge. Okay, I'm considering it to be positive and negative. As soon as you connect this potential source, there is an electric field that is generated from the higher to the lower potential, right? Now, what is happening in the initial condition? U1 vector plus U2 vector plus so on till UN vector the whole divided by n is equal to 0. We know that the average of initial velocities of all these electrons put together is going to give you a null vector. Am I right? So when this is the scenario, as soon as you connect this potential source, what is going to happen? After the connection of potential source, what will happen? Due to that electric field, there will be a force experienced by the charged particle, which is going to be E into E. Now I'm adding the negative sign. So E into E with the negative sign. Can I say that this value is equal to mass into acceleration? Which implies acceleration is going to be equal to minus of E into capital E divided by M. Accepted? So What is happening basically? Initially, each electron was possessing the velocities u1, u2, so on till un, and they started accelerating at the same rate. Okay. So when they were accelerating at the same rate, can I say that the value is going to change from u1 to a higher value? Obviously, right? Some object is accelerating, then it is supposed to have an increase in velocity. So if I talk about the final velocity of the first particle, can I say v1 is equal to u1 plus a1 into t1? But the correction I need to do here is there is nothing like a1, right? Because the acceleration of each charged particle is the same, right? So from here, what is it I can conclude? v1 will be equal to u1 plus minus E into capital E divided by M into T1. Makes sense? The only thing that I need to do here is I need to write it in the vector form. Similarly, if I take for the second particle, it is going to be V2. So V2 will be equal to U2 plus, I'm not writing A2. So I'll strike off this A1 also. It is not there. You will ensure that you should not write it. Okay, I've removed it. Okay. U2 plus A into T2. So if I write them in the vector form, it is going to be something like this. So what will I write here? Which implies V2 vector is equal to U2 vector plus negative of E into capital E as a vector, the whole divided by M into T2. Makes sense? So like this, if you keep on writing, then what is going to be the value of Vn vector? It is going to be Un vector plus A vector into Tn. Right? So here I'm writing the time to be different because each particle will take different time to reach the same acceleration. Okay. So Vn vector is equal to Un vector plus minus E into capital E vector, the whole divided by M into Tn. Now what I'm supposed to do is I'll add all these values. Right. So when I'm going to add all these values, I will get V1 vector plus V2 vector plus so on till Vn vector is going to be equal to U1 vector plus U2 vector plus so on till Un vector plus minus E into E vector by M into what am I going to get? I'll get T1 plus T2 plus so on till Tn, and this is going to be the value. Right. So what I did here is I added all of them on the left hand side and the right hand side. I added the corresponding values. Right. This is where I want you to observe now. So basically what we are getting is V1 vector plus V2 vector plus so on till Vn vector is going to be equal to U1 vector plus U2 vector plus so on till Un vector plus minus E into capital E divided by M into T1 plus T2 plus so on till Tn. Right. Now I will divide it with capital N on both the sides. So when I divide it with capital N on both the sides, I converted the vector sum to average vector sum. So can I give a name to this called as average final velocities? But we know the fact that the average of initial velocities in the vector sum is going to be a 0. Right? And if you see, I have taken the average of time. So each of them is given a specific name. This is given a name called as drift velocity. This is what is called as drift velocity, which is written as V with a subscript D and a bar on top of it, is equal to minus E into capital E divided by M into the average of all these values, the average of all the time taken by each particle to reach the same acceleration, which is given a name, which is given the symbol tau, and the name of this symbol tau is called as relaxation time. It's called as relaxation time. So relaxation time basically in terms of electrons means it is the time between two successive collisions. So the time that is existing between two successive collisions is what we call it as relaxation time. Let's visualize what I'm trying to say here is this first particle, there's a second particle. Okay. The first particle is coming and hitting the second particle, going back again. So first collision has happened. Right, going back again it will come and hit no. So the time that is existing between the first collision, going back again and coming back for the second collision is what we call it as relaxation time. Are you able to understand? Right? So this drift velocity is mathematically represented as minus E into E vector divided by M into tau. So the name of the topic is drift velocity. Which is represented by the symbol Vd. So drift velocity is minus E into E vector divided by M into tau. Right. So how did we get this drift velocity? Which term was replaced? We replace the average of all the final velocities. So when you say the average of all the final velocities attained by the particles under the influence of electric field. This average was attained only because of the electric field. If that was not there, the particles would have not experienced acceleration. If that is not there, then there is no concept of final velocity. So the average of all the final velocities achieved by the particles under the influence of electric field is called as drift velocity. If you look at the significance, right, this term will give rise to another concept called as mobility. Because this drift velocity has something to do with the mobility of the charges inside. When I say mobility, if you try to understand from the basic English, what does it state? The extent to which the charged particles are able to move, right? mobility. Right. What is the significance of it? Obviously, it helps us understand how much are the particles able to move within the conductor under the influence of electric field. Right. So basically, for me to define this mathematically, I need two technical terms in my hand. One is the result that is achieved, that is drift velocity, and the one which is driving to get that result, which is the electric field. So if you are able to define the ratio of drift velocity and electric field, then that particular ratio is given a name called as mobility. The symbol used is mu. Okay. So mu will be equal to, how do I write it? It is going to be drift velocity divided by the electric field. I hope it is clear. No? Now the question is, drift velocity is a vector quantity. Electric field is also a vector quantity. There is no concept of division of a vector with a vector. So obviously, mobility has to be a scalar quantity. So mobility is a scalar quantity. You can get these kind of questions also in MCQ. You should use this logic and then solve it. Don't memorize it. So drift velocity is vector, electric field is also a vector. There is no concept of vector divided by a vector. So it is basically ratio of magnitude of drift velocity to the magnitude of electric. So what is going to be the SI unit here, obviously? So what is going to be the SI unit? So SI unit will be drift velocity is measured in meter per second divided by, how can you define the electric field as? Volt per meter. Why we are defining here in terms of volt per meter is, we speak electric field here in terms of potential difference. We don't speak in terms of force. We could have written Newton per Coulomb also, but that's not what we are speaking. So if I rearrange this, I'll get meter square divided by volt second. So that is going to be the unit for which concept? Mobility.